Okay, is it working now? Yeah, let's start now then. Welcome to the Directors Colloquium of this February. Okay, you know that we have we try to have every month a special colloquium. This is the so-called Directors Colloquium with a coffee in the patio to have the opportunity to talk to our invited speaker, and also, okay, then, yeah, with what? Microphone is out, or is it's only for streaming? Okay, good. That should be working. Okay, our speaker today is Professor Andreas Eckart from the University of Cologne. I met Andreas. Rainer Schödel is going to make a presentation now of his scientific trajectory, but yes, let me make some comments, because it's not the first time that Andreas has been here in this institute. He did his PhD some years ago. In fact, I met him when I was a grad student, and he was already a postdoc. And his PhD was about the study of the so-called S5 polar cap sample. And in fact, some colleagues of us have made later his PhD based also in this sample. Jose Carlos Guirado, that was PhD student here, was working also in this sample. Then we have there the first connection, because we were introducing the astronomy to the work that they have already done, studying the physics of these sources. But later also we met working with the Galactic Center, and okay, we have there some contact with some VLBA measurements. And every time that he has come here to observe to the IRAM 30 meters, so just to work with some of us, he has visited the institute, and he has also presented here a seminar. Then thanks for coming many times along these years. In fact, let me mention also that this visit has been a little bit special, because yesterday he was also given a seminar at the Escuela de Estudios Árabes, yes, combining another interesting aspect of his life, because he has had always a lot of interest for the Arabic culture. In fact, he is able to speak in Arab. And okay, then yesterday he was given a seminar because in a visit that he did this year to the Emirates, where he was giving a seminar about the Galactic Center, he got to know that there was an Arab astronomer that already did some measurements about the distance to the Galactic Center. Okay, he decided to study the method that was used and make some corrections to test book that was published with some errors. Then there is a new edition that is coming and will be published in German. I think the translation in the next month. Okay, then it's I think he is naturally connected to Granada, then because of his relation to the institute, and also because of his relation to the Arabic culture and the interest for the astronomy that was already done in the old times. Okay, then. Rainer, if you want to make a presentation of his scientific career.
No, I'm just happy that Andreas is here. I worked for 5 years in his group, actually, before I came to Granada. And I remember, I think in my first or second week of my PhD in Garching, Gensel sent me to Andreas, and talking about image deconvolution and things, I got some ideas that still are at the very heart of what I'm doing right now. And yesterday, all of you lost yourself an extremely nice talk at the Escuela de Estudios Árabes. So again, but I can imagine that there may be follow-up talks to that coming here. So I strongly encourage you to go there. And yeah, Andreas is most known for his work on the Galactic Center, on the supermassive black hole at the Galactic Center. So he was involved in that research from the very beginning on, designing the first speckle cameras, doing the first high angular resolution measurements in the near infrared, doing the first proper motion measurements, and he keeps working there at the, as one said, cutting edge of science in the Galactic Center, and of course works also extragalactic work on supermassive black holes. That's just so. Of course, he has. You can look him up in ADS. A tremendous amount of publications and citations, as you can imagine. So, yeah, but let's now let Andreas speak for himself about his newest results.
Do I need a mic, or is it fine?
It's ready.
Good. Yeah, thank you very much for the nice introductions, actually. And of course, I have to stress that the work I'm presenting here is not only my work, but it's the work that was done in the group. There's several people involved, and their names will show up when the papers are being cited. And it should also be noted that now Banafsha Shahzamanian is here. She's working together with Rainer, and she has been doing polarization work on the Galactic Center. And I'm sure she will going to present some of these results at some point. It's not topic of that talk now, but it has brought us forward in the studies of the supermassive black hole in the infrared at least. So thank you very much for having me here, and I will try to summarize some of the recent results that we have produced. They basically deal with light and shadow in the galactic center, and you will find out why that is the case. So first, let's have a look at the galactic center in different wavelength bands. And what you see here basically as a large image is the galactic center as seen by Chandra. So this is basically X-ray stars and hot plasma emitting in the X-ray domain. In the very center of this map, there is located the central stellar cluster. And an infrared image that Ryan Schödel produced some years ago is shown here that shows the central stellar cusp. And we can dive into this image now, into the central stellar cusp. And if we make a zoom again into the center, then we can see the different stars that are very close to the supermassive black hole. They are of different kinds. They are late-type stars, they are young stars, they are high-velocity B stars. So there's all you can find. And this allows you to do both spectroscopy and proper motion studies over the years of these sources. And the proper motions and the radial velocities, of course, then allow you to do orbits, stellar orbits. Orbits have been published now by several groups, and we also started to get into the orbit business a little bit. And I will present some of the results that we produced along this line now in the next upcoming slides. So basically, light and shadow. What is it about? It is, as you could see, infrared light, and we can use that to probe, to use the stars that are shining in infrared light to probe for relativity in that domain, because you expect relativistic effects due to the heavy mass of the supermassive black hole, 4 million solar masses. And there's, of course, X-ray light. And Sergei star is also luminous in the X-ray domain. It exhibits flare emission. And I will say something about the shape of the flares and what you can learn from that. And it is also good for probing relativity, apparently. And then finally, I will talk about shadows, that is combining infrared and X-ray technology and infrared imaging technology with the X-ray data, and actually showing some of the physics of the hot plasma that surrounds Sagittarius A star and which it is embedded in. So that's a very nice result in terms of the global aspect of Sagittarius star and the entire region. So let's first start with the first topic, that will be using the innermost stars as a probe for relativity. And this is what I'm going to dive you through. So first of all, we will investigate the gravitational potential parameters, and namely the mass and the distance. And then I will introduce a new and practical method to investigate gravitational relativity effects in the Sagittarius star region. And then finally we go and investigate stellar orbits, both with simulated stars and with measured stars, and do post-Newtonian approximation on the orbital data measurements. And then we'll apply this to the star S2, which is one of the closest, or maybe the closest star at the moment to Sagittarius A star, and we'll see what we can learn on its orbit. And that is published recently by Parza, and Banafsha Shahzamanian was also a co-author here in APJ 2017. So all these data were taken, or most of the data, bulk of the data was taken with the NACO instrument in Chile. That's a camera that works in the JHK band, and we here concentrate mostly on the K band data. And we also combined it with, as I will go through, you will see it, we also combined it to published data from other groups, and also published spectroscopy data. So the data analysis can be summarized as such. So we did a standard data reduction, flat fielding, sky subtraction, bad pixel correction, and so on. And then there is 2 cameras that NACO has. So the S13 camera and the S27 camera. The S13 camera is used for high-angle resolution imaging of the very center. And the 27 camera, 20 milliarc per pixel camera, gives you a larger field of view. And that's very important because that includes some of the stars in the outer regions of the cluster, which are late-type stars and which have masers in their atmospheres, which can also be measured in the radio. So that allows you, the combination of those cameras allows you to tie the infrared rest frame to the radio rest frame. And then we concentrated here on the innermost stars which have long orbital sections. And we also used only data that shows Sagittarius A star flaring, so that we have a defined reference point for the orbital calculations and for doing the measurements of the orbital positions. And we concentrated on the 3 innermost stars, which are S2, which I mentioned already, which has a period of 16.2 years, then S38 and SO102, which is also a nearby star that was found recently by Meyer et al. And we mainly cover here 2002 to 2015 data with some additions. So first, connecting the infrared and radio rest frame, which is a pretty complicated business, in particular since you have also 2 cameras that need to be coupled as well. That is described in detail in the paper, and I cannot go into all the details that have to be taken into account. You have to have under control image scale, rotation, and you have to have connection stars to connect different frames with each other. So it's all very complicated. And then you have the radio measurements as well, which have also some uncertainties. But in the end, if you do the calculation, the comparison of the data, you find that if you do a reasonably good approach, as we did in this paper, then you have an uncertainty of the order of 1.8 milliarc seconds or so. That is what we could easily reach here. Other groups have reached more, finer consistency between the radio and infrared data, but for the purpose that we are after, that was absolutely sufficient for us. Then the orbital calculations, they now have to be done relativistically. So we used some of these methods to calculate orbits, namely the post-Newtonian approximation. That is, you basically make an expansion in V over C, and then you go ahead and take the strongest terms, and you can do relativistic calculations to first order, basically. So we have done that in Rubilar and Eckart in 2001, pretty early on, under the assumption that Sag A star is not moving. But in the meantime, people have been thinking about it and realized that the mass of 4 million solar masses is not that large at all compared to the inner section of the cluster, so which is also of the order of a few million solar masses of stars. And so there is very well the probability that Sag A star will do some motion, right? So it has to be left in as a free parameter. Unfortunately, that makes the whole thing a little bit more complicated, as you can see. We have now have to use the Einstein-Infeld-Hoffmann equation for proper motion. That includes proper motion as well, but it can be handled. So this is basically how it looks like. This is the data points that we introduced. We have used more data which is not shown here, which is published, which we also connected in an appropriate way. And we have used proper motion data and spectroscopy data, as I mentioned earlier. And spectroscopy is coming from Böhle et al. And from Gillison et al., as mentioned here. And then the actual orbits we did using a 4th order Runge-Kutta method that includes the deviations of the orbital motion for a better fit. And so we could go ahead and fit S2, S38, and SO102. And we did that, of course, using an MCM method, as it is done in these days. And this is one example of one fit, and that gives you the mass at 4 million solar masses and a distance of about 8 kiloparsecs. This is just one example. And it shows you also that in this MCM methodology, you see very nicely the interdependencies of quantities. Here, for instance, as an example, shown the mass-distance relation, so they are not fully independent. If you move it a little bit further away, you get a different answer to the mass. And you can see that by these linear extensions in the data cloud here. But then going to the best MCM results that we have, we find value for the mass and the distance, which is commonly found for people, for groups that do investigations of these orbits, namely 4 million solar masses and 8 kiloparsecs with uncertainties of the order of 0.1 or 0.2 kiloparsecs. And of course it gives you all the orbital elements of the individual stars. Then concerning the motion, we left it as a free parameter and can determine the motion. Here you see the data cloud and the motion that we fitted. The little fat line is our result, and the dashed line is the result that was published earlier. So we find a proper motion of Sagittarius star which can be included, which should be included for exactness, which is smaller than what has been published before and approximately in the same direction. But it's a very dicey undertaking. Then the relativistic effects that have to be taken into account, they express themselves in astrometry and in spectroscopy. And there are lower order effects like transverse Doppler effect, Doppler shift, gravitational redshift, and periapse shift. Yeah, all these effects have been dealt with in some papers which are marked here. And there's higher order effects like frame dragging or gravitational lensing that can also be included at some point. Two things have to be mentioned. That is the shape of the orbit, which is very important for this investigation. You have basically two competitive effects here, possibly competitive effects. You have the prograde relativistic periapse shift. That is due to the fact that the star moves through a strong gravitational field, and therefore the orbital elements experience some change, and that leads to a Rosetta-like orbit. It's not a closed orbit anymore, but it's a Rosetta-like. A similar Rosetta shape you get from a retrograde Newtonian effect, if there is an extended mass. Because then if the star dives into the mass, it sees all of a sudden less mass underneath itself, and that changes the orbital elements as well. So those two effects go into different directions, right? The relativistic one is prograde, and the Newtonian one is retrograde. So you have to be aware of that. If there is an extended mass, that may influence your business. If you find something which is close to the prograde relativistic shift, the likelihood that there's an extended significant mass is apparently lower. There's also other more nasty effects, right? If you get very close, like a milliparsec or so, then due to relativistic effects in combination with the spin of the supermassive black hole, the orbital plane may be changed as well. And there's even a dirtier effect. There may be granularity of a distributed mass that has to be taken into account. Because if there is extended mass, and if there is like a population of 10, 20 solar mass black holes, which is orbiting there as well, the number of those black holes will change statistically underneath S2, for instance. So there is a certain granularity in the potential that has also some effect on the orbit, and which can be of the same order as, for instance, the periastron shift, the relativistic periastron shift. All of this needs to be taken into account, and that has been dealt with in a paper by us by Sapra et al. So this is now what we did to do the investigations. What you see here plotted is basically the long axis against the ellipticity and the long axis against the distance in milliparsecs. And the dark red spots on top are all the S stars, all the high velocity stars, about 40 of them, that surround within an arc second or so Sagittarius A star. Then in yellow are the three closest ones that we dealt with here in particular. And those blue ones are ones that we invented. These are simulated stars of which we calculated the orbits, and we tried to distribute the orbital elements rather evenly so that we scan ellipticity and long axis of orbits and distances as well. And we had to stop that at a distance of about 0.1 milliarc seconds, because at that distance, that short distance of the supermassive black hole, the stars will be destroyed due to gravitational interaction. So it's not worth calculating orbits smaller than that. So these can be these orbital elements can be parameterized. Yeah, they go with ellipticity and with long axis. And you can plot them as a function of a relativistic parameter that shows the degree of relativity, basically, that needs to be applied here, or that is in action. And that particular relativistic parameter that we use has been introduced by Zucker in 2006. And that is basically, it's the shortest distance to the black hole, if you want. But it's called Y, and it's basically a Schwarzschild radius divided by the shortest periapse distance. That is a measure of how strongly relativity has to be taken into account. And in fact, it is very useful because certain quantities go with this Y. For instance, the delta omega, that is the periastron shift angle by which the periastron dials through each time the star orbits, delta omega is proportional to Y, as you can see at the top right formula. So now we have the following problem. On the one-hand side, on the left-hand side, in the non-relativistic world, things are relatively easy. You have 6 orbital elements, which are known, and you have basically a negligible computational time to calculate the orbit. So we're all happy. Yeah. On the relativistic side, it's far more complicated. So if you want to calculate a relativistic orbit, then you need to launch a star in the gravitational field. So you need to have 5 to 6 launching parameters. You need to have a post-Newtonian formalism to take into account relativity. You need to have a fourth-order Runge-Kutta method, some method to calculate the orbits in detail. And you need a non-negligible computational time to do that properly. So it's a mess. So in other words, on the left-hand side, you're happy. On the right-hand side, you get dizzy. Right? It's very complicated. So that means relativistic orbits cannot easily be parameterized. So it's not like a few or a handful of numbers that give you describe ideally the relativistic orbit. So in other words, we need a simpler method to describe the relativistic character of an orbit, and preferably a simple non-relativistic orbit fitting combined with a suitable parameterization. So we want to go back to the easy way of doing it, namely non-relativistic, but we want to be able to include the relativistic character of the orbit. That sounds strange, but it's possible. It is possible by looking at the relativistic orbit in detail. As you have seen, it's not an ellipse, it's a Rosetta shape. So it's basically an ellipse that is open or overclosed at the top. So that ellipse has a left side and a right side, so pre-periapse and post-periapse side, and it has a lower part and an upper part in the orbit. And that can be used. Those can be treated separately. Those can be fitted non-relativistically, and then you can look at the misfit or at the difference of the fits, and that difference or that misfit is then proportional to the degree of relativity and can be parameterized with this number Y. So this can be formalized a little bit, and it basically is nothing else as a squeeze state formalism. But in squeeze state formalism, you have 2 observables here, alpha and beta, which are sort of intermingled, like in the uncertainty principle, the position and the impulse. If you know the position exactly, you don't know the impulse, and vice versa. So basically, the product of alpha and beta is limited somehow by a number epsilon, right? That's an upper bound or a bound of some kind. So this is now exactly the formalism that can be applied to orbital fitting. Because as alpha and beta, you can take a probability, likelihood, that's e to the minus chi square. And as an alpha and beta, you take e to the minus chi square for the lower part of the orbit and e to the minus chi square for the upper part of the orbit. You can do the same thing for the right and left side of the orbit. And that is larger than the probability likelihood in fitting the entire orbit, e to the minus chi square. Right, this is then the same formalism, and you can go through it now. You can differentiate the different kinds of noise, of misfits. So there's noise contributions, and there is true figure-shaped misfit contributions, and you can look at them in detail. In any case, this is a measure of non-ellipticity, so of relativity in our case. And here you see a fit in which, if you fit the left and the right side, if the upper part is fitted very nicely, then the lower part shows a severe misfit, and vice versa. So basically, all you need is to do a ratio between the upper part fit, best fit, and the upper part fit under the conditions that the lower part is best fit. And that ratio then is a measure of the misfit, is a measure of the non-ellipticity, and therefore is a measure of the relativity. And if you do this calculation for these test stars, you see that actually the right trend is visible. For a higher relativistic parameter, that ratio goes exactly in the way telling you that there's a stronger degree of relativity present. So this quantity, chi square u over chi square u under the boundary conditions, chi square L goes to 1, is a measure of relativity. But there are other measures, because these orbits have, these non-relativistic orbits have orbital elements. They have long axes for the upper fit solution and for the lower fit solution. They have ellipticities, and they have a delta omega in them. So there's now 4 different ways of describing the ellipticity, which are all listed here, and we concentrate actually to the real observables, not to the misfit parameters. The A ratio, the E ratio, and delta omega. So the results now, for the simulated stars, looks like this. On the left-hand side, you see the trend for the A ratio. On the right-hand side, you see the trend for the E ratio. So that ratio between the upper fit and the lower fit shows actually a trend as a function of the relativistic parameter that allows you to say something about the misfit or about the degree of relativity. And it is largely independent of the actual E and A values, actually. So the same thing for delta omega. You see a very nice trend. It goes linearly with Y, as you would expect. And now comes the question. What is it good for? Question, is the current single-dish adaptive optics data set of S2 accurate enough to show relativistic effects using that method? The procedure would be to measure off the A and E ratios from the actual orbit for S2, and to plot them in these diagrams that we produced, and to read off the Y value, the degree of relativity, for instance. So we now go to the very edge of the plot, where the almost non-relativistic objects are, which S2 is. It's almost non-relativistic. And we can then read off, with the help of these dependencies that we found, we can read off the values for Y and for delta omega. So here's the plot for delta omega. You see there's a difference whether you take the mean values or the median values, because the errors are treated in a slightly different way. But in any case, you can read off numbers now. And you have to ask yourself the question, if you find now definite Y's, definite relativistic parameters that are close and should be close to the expected value, how significant is this result? Because you see the error bars are rather large, and further investigation is important, is required here. So what we can say is that the uncertainties for the E and A values, and for the delta omega, they are basically position uncertainties that have been transported through the connection of the reference frames to the final statement. And that means the positional offsets are the most important ones in this game. So to get the handle on this, we have taken an orbit and look at at 4 different quarters of the orbit. They typically have of the order of 7 measurements per quarter, and that, taking then a typical uncertainty of about 1.4 milliarc seconds for the position measurements, that means that each quarter can be randomly displaced by about 0.5 milliarc seconds. So we use that statistics and produce all possible random misplacements of the 4 quarters and calculate A, E, and delta omega. These are the distributions of the E ratio, of the A ratio, and of the delta omega. And you see, as an example for the delta omega, S2 is always far off the distribution. In fact, from the distribution you can read off what a 1 sigma event would be, And from this distribution, you can see that the degree of relativity that we're able to measure is in the realm of a 3 to 4 sigma result, based on these considerations. So that can be put into a nice simulation, and it basically means that for S2, we can see the difference between consecutive orbits that produce a slightly deformed orbit due to relativistic effects with this significance. It also shows you that the entire orbit can be used and needs to be used to make that statement properly. To make that statement properly, one has to mention, of course, that this is all very dangerous. Even if you measure a delta omega, the delta omega value that you get may still be influenced by other effects, and in particular by granular distribution of masses. And if you look at the number of typical X-ray stars, X-ray binaries, they rise dramatically towards the galactic center. So the density of these objects, which may contribute to grainy mass, gets excessively large towards the center, probably. And one can look at this effect, and that has been done in Sabra et al., and one basically finds that a variation in the orbital elements, like in delta omega, can be imposed by this disturbing effect that is proportional to the square root of the number of stellar mass black holes with a mass of typically 10 or 20 solar masses. So that has to be taken with a grain of salt. So one has to be very careful in taking into account all these measurements. But it's very nice. It's already on the good side that we get a value that is close to what we expect, because these are the results now. We get a mass, which is 4 million solar masses and 8 kiloparsecs distance. We get a delta omega of the order of 14 arc minutes, plus or minus 7 arc minutes. The 7 arc minutes is a nominal error. It is probably too large because of the statistical investigation that I presented. It's probably closer to 3 or so. We get, and then delta omega expected that you can calculate, which is nominally 11 arc minutes. So we are in the same realm of what is expected. And the Y factor we get, the relativistic parameter, which is 0.0008, very close to 0.0006, 0.0007, which is expected from theory. So we are close. So summary, we use 3 stars to give the mass and the distance and calculate in a Newtonian and post-Newtonian solution. We introduced a new method to get a handle on relativistic effects, which is not computer intensive, which can be handled easily. And we get values that are very close to the expected values of S2 in terms of relativity. So all of this, of course, has great potential to be improved. Yeah, it will be improved by different methods, more data, more instruments, and so on, which are coming up. In particular, there's great hope that the gravity experiment that monitors the flyby of S2 next to the galactic center, next to the supermassive black hole, that it will happen this year in detail, and that they will come up with a number, or we will come up with a number, which is probably much nicer than this. So, having had that taste that you can use stars to probe the relativistic environment of a supermassive black hole, you can ask the question, can it be done better? Because the stars, like S2, as I mentioned, the Y factor is basically the inverse of the periapse distance. The Y factor is still pretty large. It corresponds to 1,500 Schwarzschild radii or so. How about having a method that allows you to probe the relativistic mass at short distances to the black hole, namely 2 or 3 Schwarzschild radii? And it appears that that can be done. For this, we analyzed, at that time, the 4 brightest X-ray flares from Sagittarius A star and looked at their shape and modeled the shape with a relativistic model. And one should mention, since this works very nicely for the X-ray flares, it is most likely that it is also a liable method for the very bright infrared flares, which needs to be demonstrated still. This is the model. You have a black hole, you have a spot that is luminous and emitting, and it orbits the black hole. And then there's 2 important points. One point is when the spot is behind the black hole, that is characterized by the L's. This is when lensing occurs, and the light is being amplified or dimmed by lensing. And the other point is a little bit further in the orbit. This is when the maximum Doppler boosting occurs. And these are the D's in these plots. So these are competitive effects that produce flux deviations. And the typical light curves look like this. Yeah, you see basically light curves for a spot that is living as long as an orbital period and makes one event that produces a light curve which has, depending on how it moves, yeah, what inclination, what distance, that makes a light curve that has a shoulder, which is stronger or less strong, depending on the geometry. In any case, we can use these shapes, these characteristic shapes, and fit the X-ray light curves. Just boldly fit the X-ray light curves. And these are the results of those 4 flares that were known at that time. You can see, if you compare it to the fits, that they all show an indication of having this shoulder, right? But it becomes really very nice if you look at one of the latest bright flares on the right-hand side by Ponti et al. That showed a very high peaky shoulder, which you could also see in one of the plots. So in other words, the shapes of the X-ray flares resemble the flare shapes that you get from this relativistic orbital model. And now comes the interesting part. You can take this relativistic orbital model, which needs a mass, but you can set it to 1, and calculate the shape, and just use the shape and fit with that shape the flare. And then you can use the observing time, the time length of the flare, and feed it into the model to scale it, to make it from scale-free to scaled, and then you introduce a mass. So in other words, using that fitting method, you can get a mass estimate of Serge star. And this is the formula that you have. It's basically a mass is proportional to the ratio of observed time to simulated time that you use for the fitting. And this is a distribution of masses that you get from multiple fits with different inclinations and so on to the flares. And you can calculate a median and a median deviation, and you get, as a median, 4 million solar masses. In tabular form, it looks like this. So the first 4 rows in that table are the fits to the different flares. The uncertainties are strange, but they're mostly dependent on the way we do it, the way, the fact that we use this histogram and calculate the median deviation. But the medians come out to be very close to each other. If you just take the medians and median them or average them or whatever, you get a much smaller error indicating that the method is in itself is consistent, and then you get 3.5 plus or minus 0.2 million solar masses, which is amazing because you have been using this strange model fitting the X-ray flares and you get the right mass. That raises the question whether it can be applied to another object, another supermassive black hole, under the lemma that the variability you see in that black hole is very likely due to a geometrical variability, that is orbiting matter that emits, rather than a variation in the accretion, for instance. That cannot be fitted with that model. But there's one case, namely J1034 minus 39.6, that showed at some point quasi-periodic oscillations in its X-ray emission. And we just choose to pick one period, fold it back, and fitted that one period with our method, and we get something like 1.4 million solar masses, quite in the realm of the other mass estimates from other groups using different methods. So we are in the same ballpark. So, in other words, what do we learn from this? The fact that this model works implies that something must be correct with this model. So it is very likely that some oscillation at the last stable orbit or some orbiting matter is involved in producing this flare, and therefore allows us to calculate back the black hole mass. Now the last project, the third project, is was sort of a fun project. I had Emmanuel Moussous from the Strasbourg group on her traveling to Liège to a new position for 3 months in Cologne, and we thought we should do something together. And she had been working on variability of Sagittarius star with Chandra data. And as one result, she also had a very deep Chandra image that looks like this. Now this is almost 5 megaseconds of Chandra exposures. So that's the deepest you can get with a high angle resolution. And we looked at this and thought of what we could do. So we looked at this and said, there's something funny. This looks like as if there could be something. Namely, if you look at this and if you know that there is something called the circumnuclear ring around Sagittarius star, then you can see it. You can see it in the flux depressions at those locations. With respect to a homogeneously assumed distribution of the underlying diffuse emission, these fluxes are depressed. So what we did is design an algorithm to make an image of this CND in its shadow against the plasma emission. And the algorithm is very simple. You have to come up with a first-order model of the diffuse emission. You subtract the model from the image. You invert it, because it's going to be a shadow, so it's negative in flux. You invert it, clip it, everything you throw away below zero, and smooth it. And then you get an image. And we did this, and surprisingly, we got a very nice, so this is the model, the background model we subtracted. It's a symmetric model, although the stuff is asymmetric, but it doesn't really matter. Because what you find is that the image you get to the lower right is rather independent on the shape and the size of the assumption of the underlying background emission. It only has to be reasonably flat and at an approximately correct level. Then you automatically get an image of the CND. That it is an image of the CND, one can convince oneself by comparing it to other images of the CND. As you can see in the top 2 panels, it compares very nicely to an image of the CND that we obtained with ALMA data. So this is molecular line emission coming from the CND, indicating dense gas that is doing some absorption of some background, also X-ray background. That's why we get back the shape in the X-ray shadow. And you can also compare it to optical images or infrared images, as has been done in the lower part. And there you see that, first of all, there's individual dark spots here, dark cloudlets, which apparently also show up in some cases here. And most interestingly, the circumference of the bright stars here as a dashed, hardly visible dashed line is exactly the same as the circumference of the inner region that is surrounded by the shadow. So in other words, this shape of bright stars that are emitting is manipulated by a shadow effect of something that casts a shadow. And this is the CND. And this is reflected in this X-ray image of the CND. So as such, it is a nice result, but you can actually use it now to place your apertures to determine the properties of the interstellar medium in the vicinity of the Sagittarius A star black hole from X-ray data. Because you also have sufficiently deep data that you can derive X-ray spectra and get plasma properties. And so we defined offset regions and regions of stars to be excluded so that we get an image of the, or a measure of the underlying diffuse emission. As you can see here, so individual sources surrounded by red circles were taken out. And then you could get spectra in different annually around Sagittarius A star. Now scanning the inner CND region, the on-CND region, and the outer CND, the region outside the CND. The fitting again was done with an MCM method. And you see very high signal-to-noise spectra with lines on top giving you information on the abundances as well. And so you get a measure of the temperature as a function of position, of distance of Sagittarius star in terms of KT, and you get also information on the column density of the plasma. You can put that into tables, which you can hardly read here, but the tables are nice and consistent. But you can put this into a model, and the model looks like this. So basically, we have Sagittarius star in the middle, surrounded by the stellar cluster, and then we have a bubble of hot gas, which is inside the CND. The CND, as such, is colder and works as a barrier for the inner gas, and then outside the CND, there's the rest coming. And it's heavily influenced on one side by supernova remnants in that region. So you can also attach numbers to it. So basically, what we did is a two-temperature model that gave the best results to these individual regions, and you find that the inner region and the outer regions are best fitted by a low temperature and a high temperature component. So this is hot gas, whereas on the CND, you only require a low temperature and don't require a hot temperature component. So the temperature in the CND region is lower, as you would expect it, since it is denser and it has a lower column density in plasma, but it is denser in molecular gas and colder. So, summary, light and shadow towards the galactic center. So, that tells us that you can use these various methods to investigate the physics of the environment of a supermassive black hole using stars and plasma. And topic 1 and 2 tell you that both the stellar motions and the bright flare shapes in the X-ray domain indicate a relativistic environment due to the large supermassive black hole mass. And the topic 3 tells you that the extended hot plasma environment of Sagittarius star is indicative for a two-temperature model for the hot plasma with a denser and cooler CND confining the hot plasma around the central stellar cluster. That is, I think, the end. Thank you very much.
So it's time for questions.
The lifetime of the plasma blocks. They are, living for no time or in a second?
Yeah, that's a very good question. It's also a very difficult question to answer. Typically, in these models, one assumes that the blob has a lifetime which is a fraction of an orbital time scale. One can justify that. There are calculations of plasma flows orbiting supermassive black holes that indicate that some fluctuations can have lifetimes which are up to that order of magnitude. But everything else would then be stretched and torn apart, right? Or would result in a shorter lifetime. But this is actually a salient, important point in the assumptions that the lifetime is long enough to produce that flare. So it must be a good fraction, like a third or so, of the orbital time scale, and then you get it. If the blob is then not in this region during its lifetime, that is subject to lensing and Doppler boosting, then you would hardly see any variation from it. And it would just result in some noise contribution, right? But not in the bright flare. That's why I think this method only works for bright flares, because then you have the clean boundary conditions that you can apply that method. For the rest, it's noisy. It's just noisy. But that's why I said, that's why I'm very, very, very careful and skeptical here. It's not necessarily a blob that is orbiting, but it may be some oscillation at the inner edge that is at the last stable orbit, as you find it in QPOs, that he has some overbrightness that could be interpreted as a blob. So something is moving, that tells me. Something is moving, otherwise this wouldn't be working.
I also have a question with respect to the second topic. I was a bit puzzled by this formula that the mass of the black hole is proportional to the observed time divided by the simulated time. How can this be? Maybe I've missed something, sorry, but the simulated time seems something we are doing. So
the shape of the light curve, yeah, can be produced in a scale-free model. So you can take a random mass and produce the same shape of the light curve if everything is scale-free, right? And you take only the shape and fit the shape to the observed models. And you have to do that by stretching your previous time that you used to the actual observed time scale. And if you do that, that is equivalent of implementing a different mass than the one that you used before. So the ratio of times is actually a ratio of mass. The mass that you assumed before compared to the mass that you actually get. So it's the same thing here. So you go from a scale-free model to a scaled model, and that involves the time and therefore involves the mass.
A quick question: to which precision do we know the mass of the black hole in the galactic center by now?
Yeah, how well do we know it?
Because from the masses you showed in this part also, it seemed that this method gives like a factor of 2 differences. Is that the precision we know, or is it just...
The new method that I showed that works with the X-ray flares, part of the error is given by the method how we derive that number. Right? We have an ugly distribution and we take the median and the median deviation, and that gives an ugly uncertainty. But that has nothing to do with the true uncertainty, it's just the distribution. The choice of the method is reflected here, so the method-dependent contribution. Because if that number, if that uncertainty would be real, it would be highly unlikely that you get 4 times the same central value. Right? So what we actually do then is we take the central values and calculate the spread along the central values, and that comes out to be 0.2. Right? But it's not exact, it's not beautiful, but it works. Right? And the other mass estimates that I showed from the orbital calculations, that is also not straightforward. I mean, you can do it easily, quote unquote, using Keplerian orbits. Yeah, then you get a mass with a reasonably small uncertainty. But as soon as you open up for relativistic effects, you allow the model and the fit to drift a little bit into different regions, and you typically get a slightly larger distance and a slightly larger mass due to the structure of the data sets. So that's a little bit peculiar, but everybody finds that. It was also mentioned, I think, in the Zucker paper and other papers that deal with that problem. So, yeah, we're working on it.
NACO instrument is not working very well in the last years, no? And I wonder if you are going to observe SO2 this year in the periapse, and also which instrument are you plan to use to observe and study the orbits in the next year before the new generation of telescope?
Well, we look positively into the future. I can only guess the answers to the question that you put forward. So we are in the Gravity Consortium. Yeah, so we built instrumentation for the Gravity Consortium, and we gave our guaranteed observing time to a program that measures the binary Sagittarius star S2. And from these measurements, there will be a number for delta omega coming out. Because most of this delta omega flip that happens during periapse, and that can be monitored somehow. Right? So there will be a number that will probably be at a higher significance, definitely at a higher significance than what we can derive. But our intention was to look at the available adaptive optics data and see whether it is good enough to give already a hint. And we find that it is indeed good enough, and we're working on a more precise handling of the uncertainties. That seems to be possible as well. But that's very nice, because it tells you that the effect has a magnitude that has to be measurable and can be measured already now with the adaptive optics. Not with a high precision, but with a reasonable precision that you can clearly see it being indicated. And that is what made us excited.
Hi, Andreas. Very nice talk. I'd like to know, is it possible to have a kind of an estimate of a number of objects for which you could use the same method? Because you've shown our galactic center, and in addition the object G1034 and something. But how many objects could be in principle?
Probably a very small number. I don't know. I have to. I'm not completely familiar with all the X-ray variabilities of supermassive black holes that are out there and how they are explained. Some of them certainly will be explainable due to an increase in mass accretion. Right? This is not the kind of variability that this model can handle. Right? This model can only handle geometrical effects. So I would say everything that shows a quasi-periodicity, and unfortunately this is only one object to my, as far as I know, could be treated with this method. Right? You can probably use it also for binary stars, for X-ray stars. Yeah. If you have a variability that's due to a geometric effect, and if you assume that model, it should give you an answer.
Yeah. Okay, thank you.
Yeah, I have a curiosity. In the determination of the stellar orbits, you are taking only those epochs for which Sagittarius A star is in a fluoring state.
Yes.
Okay. Could there be some dependence on, I mean, in these fluoring stars there could be some changes in the structure, and there could be some change of the centroid, of the brightness centroid, that could affect your measurements, or not, really?
I wouldn't think so. I can't give a very positive answer to this. But the difference in the difference in orbital parameters, that is the difference in the upper and lower fit, or the right hand and left hand fit, they only depend to a very small fraction of the orbits on that particular region. And I think in most of the cases, except for the very inner regions, when the periapse happens, most of the cases we can separate them well enough that we get a clear measurement of their position. But again, interferometry would of course help here, right? This is the reason why gravity has been built.
Well, I just wondered, all these flares, is this material that falls in finally, or is it material that can be ejected maybe in the form of a jet?
I don't know. We'll find out. I mean, this is the reason why the EHT experiment is running right now, the Event Horizon Telescope experiment. They want to image Sag star in the radio with highest angular resolution, and depending on what you see, you can maybe say something about what is happening there. Right? It cannot be excluded that there is something being ejected. It cannot be excluded that there is a short jet. Yeah? It's very difficult. It has not been measured yet. It has been claimed only to be present. And it can also not be included that there is something orbiting, which shows up during flare emission. So it could be a scenario that in quiescent state, in quasi-quiescent state, you see a slightly distorted distribution in the radio emission due to an enhancement on one side and a dimming on the other side due to relativistic effects. And that during a flare emission, that structure changes somehow. Either allowing you to make a stable on something orbiting, or allowing you to make a stable on something being ejected. But that is unknown. So any answer I would give would be speculative. The measurements have to be done.
Just if you follow an individual flare or a statistical ensemble of flares, could you not model the light curve of a particular flare? And
yes, of course.
More compatible with expansion.
Yes. You can do that, and we have done that. It looks like as if some of the brighter millimeter flares that are generated at a peak frequency of about 350 gigahertz, that they decay adiabatically extending to lower frequencies, and that they go along as a follow-up of infrared flares. And the infrared flares are nothing else but simultaneous flare events that take place with the 400 gigahertz flare showing up. So this is simultaneously, but the delay comes due to the adiabatic expanding and due to the fact that you systematically look at lower frequencies. That is a possibility that is supported by these calculations by these fits. There's also one other piece of information. There's one paper that we published, as Rauch et al., where we have monitored with VLBI and in the infrared CJ star. We saw an infrared flare, and about 1.5 hours later, we saw a VLBI image that was deviating from the two before and two VLBI images afterwards. So there was an asymmetry in the scattering size of CJ star. Being consistent with a small component being ejected or being present at the time where the symmetry showed up that has a different delta x of 1 milliarc second. Yeah. And that again would be consistent with an ejection that happened at the infrared flare time with a traveling speed close to the speed of light, or a good fraction of the speed of light, that would just allow within the adiabatically decaying time scale the object to show up 1 milliarc second offset from the center. Yeah. That is a nice model and a nice explanation, but what people are looking at now is if you look at images of CJ star in the radio, and if you are close to the frequency, namely 3 millimeters, at which the scattering veil becomes transparent, apparently you get speckle phenomena. That means it becomes not transparent like a murky, like a nebula that just gets transparent. There's phase fluctuations. And you start seeing for a short time, or for a short range of frequencies, you start seeing multiple images of CJ star. That could give rise to that phenomenon that I described earlier as well. So it's highly complicated. It's highly complicated, and it seems to be a feature of nature that the more you seek, the more problems you get, and the more the number of questions just rises with your attempt to answer them.
So the next talk, thank you very much.
I have a question regarding the neutron stars in this region, because you have to know very well the medium here to model it for your stellar orbits. So you talk about populations of black holes, perhaps diffuse gas. What about the population of neutron stars? Since pulsars are very interesting objects here and highly complementary to these kind of studies, I'm trying to find one here. And are there any hints in your data of population of neutron stars? And I would like to also know your opinion on why don't we detect pulsars in this region yet?
As you certainly know, towards the very center, the dispersion is very high. So it's very difficult to see pulsars. So you have to probably go to high frequencies to be dispersion-free, rather dispersion-free.
Scattering. Dispersion.
We can correct for it. That's easy. It's a scattering, I think. Yeah.
The signal you can correct it for dispersion, but you need to know what you correct for.
So in radio,
this is difficult. So that's why I would like to ask if at this wavelengths where you don't have these effects, you can.
Paper on it by us, by Seminario et al. And this is a paper on neutron stars, on the detectability of neutron stars in that region. Because in principle, you should be able to detect the neutron stars by their interaction with the interstellar medium in that region. And the best place to look for this is the mini-spiral, for instance. Yeah? Neutron stars should go through the mini-spiral and should do some interaction. Yeah? It turns out that the Bow-Shock signal and the strength of the interaction is just weak enough and small enough that you cannot see it right now. So that would be a very nice project and proposal for a 40-meter telescope, looking at this region with even higher angular resolution. And then maybe you see cometary-shaped sources, Bow-Shocks of neutron stars, going through the ISM, going through the mini-spiral and so on. But right now, it's very difficult, and I don't know a good method to see neutron stars, for instance, in the infrared or so.
Do you take them into account?
Models, or you just neglect a possible population of neutron stars in this inner part?
In the models that Sapra et al. Dealt with, the population that we dealt with is populations of black holes that have masses of 10 to 20 solar masses, because they would, in the scattering process with S2, produce a deviation of the S2 orbit, a significant one. Whereas an interaction with a neutron star is probably less harmful, because these S2 is a 30 solar mass star, typically, and 1 solar mass or 0.7 solar mass neutron star is not really changing the orbit dramatically, easily.
So last short question from Ivan. And just before we finish, so I want to mention that Andreas is still around until tomorrow. He's in the visitor's office, in the ex-office of Rodrigo, of our ex-president, so in the VIP office around here on the first floor. So of course he'll be around, and I guess he'll be happy if you come with your questions.
So the question is about estimating the density of the material very close to the supermassive black hole. So, I mean, since well, actually many years we have a project here at Iran doing millimeter polarimetry to try to measure the Faraday rotation with, I mean, time scales of something like weeks and sometimes days and so on. So is there a possibility to have more or less that time resolution on measuring the density of the material from the infrared or perhaps X-rays? Or yeah,
we are working on it. Can be done, but we're working on that. Or
it's not published.
It's not published. So perhaps we can talk later. Yes,
our results. Okay.
The result yet, but we have the method and the data, and we have a person working on it. But I wouldn't be able to say the results.
Okay, let's thank Andreas again.